212 through 215. And part of what you're going to gain from this lecture is this is going to help you with your in-class problem that I gave you on Monday. So to start out, let's take a look at that in-class problem. All right, I had you take a ball and throw it up, marking the position at which it left your hand, its maximum position, and then I also asked you some questions about when it returned to the same level at which it left your hand. So that means that the data that you analyzed or collected should have been the maximum position, the initial position, and again the final position, which you should know, or you should be able to make the connection that these two are the same position. You're going to notice that I maintained my values in the x direction, even though this is a vertical situation involving free fall. That's okay. If you want, you can choose to change all of your x values into y values. The values I asked you to find were the initial velocity with which it left your hand, the time at its maximum height, which will indicate right here, this is your Tmax, the time for the final position, or how long it took for it to go all the way up and down. Another way to talk about that is it's called air time. And then the final velocity, the velocity that the ball is when it returns back down to your hand. And I told you that in addition to the data that you analyzed, you are going to be using the kinematic equations for uniform accelerated motion, because that's exactly what this is. This is uniform accelerated motion. We know that gravity is the uniform acceleration that the ball is experiencing. So, in order for us to solve this problem, we're going to be finding the connecting concepts. One of the connecting concepts is that gravity, which is 9.8 meters per second squared, is acting on the ball the whole time, because I asked about the time that it left your hand until the time that it's at the same level that you let it go or released it. So that means that gravity is actually causing it to fall. In this situation, we are able to neglect air resistance because the velocity is low enough that that's possible. We broke it down into ball goes up and then it goes down. But before we break it down any further to solve the problems, we're going to jump in and we're going to take a look at example 2-12, the ball thrown upward. So in example 2-12, you're going to notice that it's strikingly similar to the problem that we're working on in class. It's a person throws a ball in the air with an upward initial velocity of 15 meters per second. We want to know its maximum height and the total hang time of the ball. And remember, I just pointed out this vocabulary, hang time, is the total time that the ball is in the air. So let's consider things that we know. Some of the things that we know is that we're focusing on when the ball leaves the hand. And let's talk about why it matters that we're only interested in the point where the ball leaves the hand. And the reason that we're doing that is because we want to focus on a situation where we have uniform accelerated motion. If your hand is doing the moving of the object, we may not have uniform accelerated motion. But we know that any object experiencing free fall is experiencing uniform accelerated motion. So that means that as long as our hand is not touching the ball, we will have uniform accelerated motion and all of our kinematic equations will apply. This is a really important consideration because as we move on into our next unit, when we start talking about dynamics and forces, uniform accelerated motion and kinematic equations are not always going to be the appropriate strategy for problem solving. So we only want to focus on the situation where the ball leaves the hand, goes up, and comes down. Because in that situation, gravity is 9.80 meters per second squared. All we have to do is find our other known values, set our axes, and solve. So we don't care about the throwing action. Could have been done by a disembodied hand, could have been done by you, we don't care. But we do know that, like I said before, we could break the problem down. Ball goes up, ball comes down. So what do we know? Well, we know that when we set the ball to go up, its initial velocity is 15 meters per second. We're going to set up as the positive direction and down as the negative direction. So in that situation, since up is positive, down is negative, our acceleration due to gravity is negative. Now, let's list out our givens. We know that our initial velocity is 15 meters per second. We know gravity is negative 9.80 meters per second squared. We are trying to find our maximum height, and we don't know any time, so that means that our who cares value is probably going to be time. So that brings us to the equation we could solve using v squared equals v naught squared plus 2ax. Alright, this is our equation when we don't care about time or don't need to know about time. We know our initial velocity, so we can go ahead and plug in. Oh, by the way, we also know our final velocity. Our final velocity is what happens when this ball makes it to the top. The ball will continue moving upward until gravity finally causes the velocity to be 0. In our position versus time graphs, in our velocity versus time graph that we produced on over the weekend, we noticed that this is what happens when we throw a ball, right? The ball moves from a high positive velocity in the positive direction all the way down to 0, right? This right here represents the max point. It's the maximum, where the velocity is 0, and then it changes directions and begins moving down in the negative direction. So we know that 0 squared equals 15 meters per second squared plus 2 times negative 9.80 meters per second squared. And then our x value in this case, I'm going to go ahead and I'm going to switch it to a y value for our vertical convention. That y value represents our h max. So I solved this problem. I'm going to cheat and use my cell phone because I didn't grab a calculator. And it's going to be 15 squared divided by 2. And we get 11.5. Now here, if you were not careful with your convention, if you did not make sure to set your acceleration to a negative 9.8, when you rearranged this equation to solve for y, you would have gotten a negative 11.5 meters, which would have suggested that the ball moved in a downward direction. And that's not what happened. So make sure to double check your conventions. We've found the maximum position of the ball. We can also now calculate the air time for the ball. Alright, so we want to find the hang time or the air time of the ball. We could keep this problem broken into the ball goes up and then the ball comes down, but what we want to do instead is we're going to consider the whole time interval, the time of the ball going up and down. So our knowns, I'm going to move this up so that you guys can see it. Our knowns for this situation are that our initial velocity is 15 meters per second. Our acceleration due to gravity is negative 9.80 meters per second squared. We also know that our position is 0, right? Because the ball started here and it ended there. So that means our delta x is 0, or delta y in this case. So our position is 0 meters, and we're trying to solve for time. So our who cares value here is our final velocity, and we are then going to be using the equation y equals v naught t plus 1/2 g t squared. So we set y to 0, our position is 0, and we have 15 meters per second times time plus 1/2 times negative 9.80 meters per second squared times time squared. Now, this is a squared equation, and we can solve this by factoring. So I'm going to factor out our time. 0 equals 15 meters per second plus 1/2 negative 9.80 meters per second squared times time times time. And now we have a couple of options. One of our options is that time equals 0. Another one of our options is that time equals 15 meters per second divided by 1/2 of g, which is negative 4.90 meters per second squared. So that means that our time would equal 3.06 seconds. So that means that there's two answers because we had a time squared function, and we could say that, well, it took the ball actually 0 seconds to be at the position of 0, or it took the ball 3.06 seconds to return to the position 0. But realistically, we know that there is only one correct answer, because we know that the original time that the ball was at position 0 times 0 has already passed, so we know that it takes the ball 3.06 seconds to return to that position. And that solution is the real value. And so you're going to have to use some logic when you're problem solving like this. When you can technically solve for two time values, you're going to have to decide which is the practical time value to solve for. So moving onward, we'll still come back to our complex problem solving in our class problem. But before we do that, we're going to talk about conceptual examples. Alright, so this is 213 conceptual examples. There are two possible misconceptions that happen when we talk about objects being thrown or objects that move. One of the first misconceptions is that acceleration and velocity are always in the same direction, and this just isn't true. For example, you could take a car. I swear that's a car. She's moving really fast. Alright, if the car is moving with its velocity in the positive direction, how could that car end up stopping? Alright, well, if the car stops, then that means that the velocity has to go from a high magnitude to a velocity of 0, which, consider plotting that, it would look like that. Alright, clearly the slope of this graph is negative, which means that the acceleration is a negative value. Alright, exactly how large that negative acceleration is just depends on the magnitude of the slope. Alright, so that's one example. Another example is objects getting thrown up, like the balls that we've been looking at. Alright, so in this situation, if we throw a ball up, eventually what goes up must come down, which means that at the top, right, when the ball goes up at the top, the velocity must have gotten to 0. So here we have another situation that's very much the same, where in our velocity versus time, we started with a velocity greater than 0 in the positive direction, if we consider that the positive direction is up, and it slowed down to the point of stopping. So those are two great examples of acceleration and velocity being in different directions. The other misconception that at the top of a throw, right, like you throw a ball up in the air or you get ready to drop a coin or any of those situations, one of the things that we think sometimes is that there's 0 acceleration at the highest point. So on a projectile pathway like this, like something goes up, then it comes down. At the top right here, we know that our velocity is 0. That's the point at which we have an object that changes direction. So one of the concepts or ideas is that acceleration equals 0 too. That can't be true, because consider, have you ever thrown something and as soon as it gets to its highest point, it just stops and hangs out there? No? That's never happened to you? Well, anything that reaches its highest point and then comes back down has to have something causing it come back down, and that something causing it to come back down is acceleration. So we've talked multiple times now about the position versus time, the velocity versus time graph, right? Where when something reaches its highest point, its velocity is 0. Well, it comes back down, which means that it goes from a 0 velocity to a larger velocity in the negative direction, right? This is the positive direction, this is the negative direction, right at that highest point, at that max point. All right, so what happens here is, oh, look, the slope doesn't change. Oh, look, there is a slope. All right, so this whole graph, you've got a non-zero acceleration. There is a slope, and that slope has a value, so that acceleration is not 0. So that's the other misconception that we want to make sure that we don't fall into that way of thinking. So then we can move on to another example. Something else that we need to consider is a ball getting thrown upward. So we're going to take the same ball as in example 212, only this time the ball is fluffy and its name is Gil. So we're going to calculate a few things. We're going to calculate the maximum time, the time that it takes for Gil to make it to the top. All right, so that means we throw Gil upward, right? And then at his maximum height, we want to know how long that took. That's the first thing that we want to know. And then when Gil falls back down, we want to know what his velocity is down here. I think Gil's kind of scared. He's fluffy, but he still doesn't want to hit the ground. Alright, so first one's pretty respectably easy. Right, we know a few things. Our givens. Our initial velocity is 15.0 meters per second. This time we know our height was 11.5 meters. We calculated that in 2-12. And we also know in this situation that our acceleration due to gravity is negative 9.80 meters per second squared. And we know that our final velocity is 0 meters per second. So we have a couple of options. We're trying to find t. So we want to use the simplest possible equation. And so that would be, in my estimation, this one. Alright, even though it doesn't include our position or displacement, it's still an equation that would work. We could use another equation that relates velocities to position. For example, we could have used y equals 1/2 v plus v naught times t. That would also work, but I want to use this one just because. Alright, so our final velocity is 0, and that's going to equal 15 meters per second plus the acceleration, negative 9.80 meters per second squared, times time. I solve for time, and I'm going to get that time equals 1.53 seconds. All right, one of the really cool things to note here is our total hang time was 3.06 seconds, and this right here is exactly 1/2 of our total hang time, which means that we've found a fundamental concept for all objects experiencing acceleration due to gravity or free fall motion. And that is, for objects that are thrown up in the air, the hang time is made of 2 equal parts, because the acceleration going up is going to be the exact same as the acceleration going down. The acceleration is the same in both directions, so that means that the hang time is divided perfectly evenly between the time the object takes to make it to the top and the time it makes it to go all the way back down. They're absolutely 100% of the time always going to be equal, because what's true the entire time that the object is experiencing its motion? It's experiencing acceleration due to gravity, covering the same position up and then down with the same uniform accelerated motion. And we can also calculate the ball's final velocity. All right, well, we can consider a few different things. I'm going to use the very simple equation, v equals v naught plus at, only I'm going to be very careful when I set my values. All right, this time I'm only going to be considering the situation where the ball comes down from the top max position, there's Gil, all the way to the bottom position. So we know that the initial velocity in this situation, for where Gil starts right at the top, that initial velocity is 0. Right? That's why he's coming back down. I also know that acceleration due to gravity is negative 9.8 meters per second squared, and I know the time. Right? The time is the hang time. But it's only 1/2 of the hang time, so that means that I know the time is 1.53 seconds. I solve in this equation, and I get that his final velocity is 15 meters per second. Hey, wait a minute. Isn't that the exact same velocity as he started with? Yes, it is. Now, let's see. I want to choose different givens. I'm going to choose, does it change it if I consider this is my initial velocity, this is my final velocity, and I'm going to use my whole hang time. So then I'm going to say v equals 15 meters per second plus negative 9.80 meters per second squared times the hang time 3.06 seconds. And I solve that, and I get that the final velocity is 15 meters per second, and it's a negative value, and that should be a negative value too. Sorry about that. Oh wait, these two answers match, so not only have I checked my work, but now I have this fundamental concept in addition to my hang time concept. I can consider, oh, when an object is thrown upward and then it comes back down and it reaches the same position, right? It means that the velocity here should be equal to the velocity here, because the whole time it was going up, gravity was acting on it, and that's a constant uniform acceleration. And up here, the velocity is 0. It's 0 for the first situation. When the ball was going up, velocity up here was 0. When the ball was coming down, the velocity here was 0, which means that there's some uniformness about this situation. Right? The kinematic equations for the first half are going to be the same but opposite as the kinematic equations for the second half, and we must make sure our axis stays consistent the whole time. So that should give you some really good, thoughtful material for us, and we're actually going to be jumping back to our in-class problem solving. Right? So a few things that we can talk about when we're breaking things down into our connecting concepts. Gravity is 9.8 meters per second squared the whole time. We're going to establish down as the negative direction, so that will have a negative value. Another concept, the ball goes up, then it goes down. I've shown you that no matter how you choose your situation, you can get the same answer. But we can break the problem into two pieces. All right, first piece, all right, starting from the ball at the bottom. At the top, we know that the final velocity is going to be 0. We could figure out that time, and we know that the acceleration is going to be due to gravity. This is our position change. You could say x or y, depending on what direction you're using your axes. So that's ball goes up. And then situation 2, when the ball comes down. You know here in situation number 2, your initial velocity at the top is 0. Acceleration is still due to gravity, and we could determine the final velocity of the ball down here, and we could figure out the time it took the ball to go from here to here. Now obviously the sum of the time it took the ball to get to the top and the time that it takes the ball to get to the bottom will equal the whole time. Alright, the top in this situation is the connecting point between moving up and down. If you break the problem down into two situations, you have the top that will connect situation 1 to situation 2. But as we looked at, we can always solve the problem as a whole. It just means that we're going to have multiple answers in those situations. So since we have multiple examples in those situations, we can apply the quadratic formula. So before we do that, in our last example problem, let's talk about reporting acceleration. So acceleration is often reported in terms of g's, right? And so g's, you've probably heard of it before. He was pulling so many g's when he made that turn. Is really just talking about acceleration, and there's a screwdriver, in magnitudes of 9.8 meters per second squared. Sorry about the focus. So we'll try that. Come back to life, my friend. Come on, bro. Don't do this to me. There it goes. Alright, so it's just acceleration in magnitudes of 9.8 meters per second squared. For example, if you've got an airplane that pulls out of a free fall, and it pulls 3 g's out of that free fall, that means that it's accelerating that 3 g's is equal to 3 times 9.80 meters per second squared, or its acceleration was 29.4 meters per second squared. Alright, one of the things that makes it convenient to talk about acceleration in terms of g's is the fact that we can relate how many magnitudes of force of gravity a human body can resist, and we'll talk about that more when we talk about dynamics too. So another example, you're driving a car, and when you get on the freeway, you're pulling 0.5 g's. Well, if you're pulling 0.5, we'll say 0.50, two significant figure, g's is going to be equal to 0.50 times 9.80 meters per second squared. That means you are accelerating at a rate of 4.9 meters per second squared. Go you! Super quick! And so that's how you report. If you have a value, like say you are accelerating at a rate of 20 meters per second squared, or if you were going to report that in g's, you'd take that 20 meters per second squared, divide it by 9.80 meters per second squared, and you'd get your magnitude of acceleration in g's. It's just going to be 20 divided by 9.8, which is going to be 2.04 g's. Okay, so that brings us to our last example for this video. And the last example for this video is using quadratic formula, right? When there's more than one time that could be the solution for the same problem. All right, so we're going to take a look at Gil. The ball thrown upward, part 3. We're going to calculate when Gil passes a y value of 8 meters above Benny's hand. And then we're also going to calculate or determine how do we know it was Benny that threw Gil. By the way, I can't decide how Gil's name is spelled in case you didn't notice. Alright, so let's go ahead and let's consider this situation so that we can figure out how we know that Benny threw Gil. Alright, so first things first. We know that Gil moved upward until he made it to 8.00 meters above his 0 point. So we know that we can use the equation y equals v naught t plus 1/2 gt squared. Alright, because we know that acceleration was due to gravity, negative 9.0 meters per second squared. We know the initial velocity was 15.0 meters per second. We don't know the time for that 8 meters. That's what we're trying to solve. But we do know that the position is a positive 8.00 meters above its starting point, right? Because up is positive. So now let's solve it. 8.00 meters equals 15 meters per second times time plus 1/2 g, that's negative 4.90 meters per second squared times time squared. Alright, now, the only way to solve this is using the quadratic equation, which is set the whole thing equal to 0. So you've got negative 4.90 meters per second squared times time squared plus 15 meters per second times time plus minus 8.00 meters equals 0. And now that you've done this, you know that your only solution is t equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Well, how are we solving that? Let's break it down. This is a, this is b, this is c. So when we plug it in, right, we rewrite it in the form of quadratic equation. We plug in our values, and we get 2 answers for t. Right? T is going to equal (15 meters per second plus or minus the square root of 15 meters per second squared minus 4 times 4.90 meters per second squared times 8 meters all over 2 times 4.90 meters per second squared. And you're going to notice that these are set to positive values because that's a negative, cancel out to be a positive. You get 2 answers. Your 2 answers are that the time could be 0.69 seconds, or that the time could be 2.37 seconds. In this case, we have to ask ourselves, are both of these solutions valid? And the answer is yeah, both of these solutions are probably valid. So let's talk about why both of those solutions are valid. All right, first of all, neither of them is negative. So since it didn't happen back in time, then it must work. All right, so imagine then that we actually plotted these. Remember, our max was 11.5 meters. seconds, which means that the ball moved up and then the ball came down, which means that along the way, here's your 8.00 meters, right? Here would be the time 0.69 seconds that Gil hit 8 meters on the way up. And here would be the time 2.37 seconds when Gil was on his way back down. So sometimes you have two solutions for a quadratic formula, and both of them are valid because that position, for example, in this case, happened twice. Once on the way up and once on the way down. And then the next question was, how do we know that Benny threw him? There he is, Benny. Your hand is so creepy. Why is your other hand coming out of your body like that? Benny, you... This time his shirt is a disembodied spelling of his name. Well, we know that the initial velocity was 15 meters per second, and Benny threw poor fluffy Gil up. Well, it just so happens that 15 meters per second is, oh, Benny's levitating. Look out. 15 meters per second happens to be hold on. 15 times 1600 15 meters per second times 1600 meters, 3600 seconds. 15 times 3600 divided by 1600, 33.75 miles per hour, and Benny threw him up, so that's how we know.